Welcome back. We start this video with the following definition. If A is an element of a group G, then define um, the subset of G generated by A to be the set of all integer powers of A. So this is the set. I have a typo here. I don't need two equality signs here. So this is the set of all integer powers of A, including A to the 0, which is by definition the identity element of G. And we are using this, we are writing A within the inequality symbols here. And so we call that the subset of G generated by A. And if the group operation is denoted by addition, then the subset generated by A would be this collection of all integer multiples of A. So this would be things like negative 3A, negative 2A, negative A, identity A, 2A, 3A, and so on. If G is a group and A is an element of G, then the subset generated by A is a subgroup of G, and it is called the cyclic subgroup of G generated by A. A is called a generator for this subgroup. So why is this a subgroup of G? Well, that's pretty clear because if you multiply two powers of A, you get a power of A, and the inverse of each power of A is also here, right? So the inverse of A to the 3 is A to the negative 3, which belongs to this set. So this set it satisfies the closure property, and also every element of this set has an inverse within the set. So this is a subgroup of G. The group G is called a cyclic group if there exists an element A in G such that the subgroup generated by A is equal to the entire group G, in which case we say that A is a generator of the group G. If K is any subgroup of G and A is an element of K, then the subgroup generated by A is contained in K. And this is clear because K being a subgroup of G, it is closed under the operation. So if A is in K, then any power of A will also be in K. Notice that Z is generated by 1, and also it is generated by negative 1. Because any element of Z, remember Z is a group under addition, and every element of Z, you can think of each element of Z as a multiple of 1 or a multiple of negative 1. So what is 3? Well, 3 is 3 times 1, so it's a multiple of 1. But 3 is also a multiple of negative 1 because 3 is equal to negative 3 times negative 1. So it's a multiple of negative 1 as well. So Z has, in fact, two generators, 1 and negative 1. So Z is a cyclic group then under addition. And these are the only generators. If you think about it, you'll see that there are no other generators in Z. In Z10, what is generated by 2? Well, in Z10, you look at all. Z10 is a group under addition. So to see what's generated by 2, you simply take multiples of 2 in Z10. So, for example, 0 will be in this subgroup, and then 2 times 1 is there, so 2 is there. 2 times 2 would be 4 is there. 2 times 3 is 6. 6 is there. So 2, 4, 6, 8 is in there. So 0, 2, 4, 6, 8. Those are the multiples of 2 in Z10. And that's the subgroup generated by 2. Zn is under addition is a group, and it is a cyclic group which is generated by the element 1. So for example, Z10 is generated by the number 1 because every element of Z10 is a multiple of 1. Okay, so in this example, we want to show that every subgroup of Z is generated by a single element. In other words, every subgroup of Z is cyclic. Okay, so let's let H be a subgroup of Z under addition. If H is the subgroup containing 0 only, then we are done because H is cyclic. So if not, then H must contain some positive integers. And by the well ordering, that is, if H is non-empty and it's a subgroup of Z, then some of the elements of H must be positive. And so for example, if you say that H has a negative inverse, but because it's a subgroup, the inverse of that would be positive and must be in H as well. So H has some positive integers if it is not this subgroup. By the while ordering principle, then H has a least positive integer, and let's denote that by D. Now, if I take any element A in H, that's going to be a multiple of D. And why is that the case? Well, if I take any element of H, then I can divide that by D, and I can get a quotient and a remainder R, and R has to be less than, R is non-negative and R is strictly less than D. And this is by using the division algorithm. So from this, I see that R is equal to A minus D cubed. Now, because A belongs to H and D is in H, therefore any multiple of D is also in H. So remember, D is the least element in H. So D is in H, so any multiple of D is in H, A is in H, so A minus DQ is in H. So therefore R is in H. But R is strictly less than D, and D is the least element of H, so then R must be 0. And so as a result, if R is 0, we see that A is DQ, which tells you that A is a multiple of D. In other words, we have shown that every element of H is a multiple of D. So as a result, we see that H is generated by A, and therefore H is cyclic. So we have shown that every subgroup of Z is cyclic. So if I look at Z10 star, which is also sometimes denoted by U of 10, I want to show the Z10 star is generated by 3. Therefore, Z10 star is a cyclic group under multiplication. So Z10 star is a group under multiplication, and it is cyclic generated by 3. To see why that's the case, we just take powers of 3 and see that we get all elements of Z10 star. So recall that Z10 star would be the numbers between 1 and 10 that are relatively prime to 10, and these are 1, 3, 7, and 9. And notice that 3 to the power 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, and 3 cubed is 7. So you see that the powers of 3 give us all the elements of Z10 star, and therefore Z10 star is generated by 3, and it's cyclic. So again, this is under multiplication. If I look at the set of 4 elements, 1 minus I in the group of non-zero complex numbers under multiplication, then this is a cyclic subgroup and it is generated by I. So C star is a group under multiplication, and this is a subgroup of C star, and this is generated by I. And you can check that that I to the 0 is 1, I to the 1 is I squared is -1, and I cubed is -I. And if you look at powers of I beyond that, you will keep repeating this for 4 elements. Okay, so I'm going to stop my video here. In the next video, we'll be looking at subgroups generated by more than one element.